Significant figures have to do with how many zeros that there are and where those zeros are located. So numbers that are always significant are non-zero digits, captive zeros, and trailing zeros. Trailing zeros are zeros that are to the right of a decimal place, uh, and when they're in scientific notation. This gets a little bit complex, I think, when we're talking about significant figures. It is part of science. It is part of what we do and how we calculate. Um, but I'm going to go through this section a little bit more quickly uh, because I believe that significant figures, while they are important, uh, learning more about chemistry is also important. So um, the numbers that are not significant, they're always not significant, are leading zeros and trailing zeros. Um, so trailing zeros when they are to the left of the decimal place. So the numbers that are always significant are trailing zeros when they're to the right of the decimal place, and the numbers that are not significant are trailing zeros when they're to the left of the decimal place. Also, the numbers that are always significant are trailing zeros when they are in scientific notation. This is a captive zero. It's in between two different values. This is called a trailing zero. These are leading zeros, captive zeros, and a trailing zero. All right, so significant figures in these calculations. Results calculated from measured numbers are at least as uncertain as the measurement itself. So when we add or subtract numbers, we have to round the result to the same number of decimal places as the number with the least number of decimal places. So whatever the least decimal place is, that's going to be what our final value is. So if we are adding something that is like, let me think of an example here. If we are adding something like 3.65 and 1.2, we get an answer of 4.85, but we actually are going to write our answer as just 4.8. So the least amount of decimal places is how we're going to report our answer. But we would probably round that. So if it was 0.85, we'd round that to 4.9. When we multiply or divide numbers, we should round the result of the same number of digits as the number with the least number of significant figures. So the least precise value in terms of multiplying or dividing as well. So same rules apply for adding and subtracting as they do for multiplying and dividing. If the digit to be dropped is less than 5, we round down. And if it's more, then we round up. If it is 5, we round up or down, whichever yields an even value. So for that last example, I did not do that correctly. Our value was 4.85. And we have to yield an even value for our retained digit. So even though this is a 5, normally we would think, oh, we round up to 4.9. But we want to have an even value of our retained digit. That means the digit that's left over, we want to be an even value. So this is 4.85. So we're actually going to round down to 4.8. Now, if we had something like 4.75, then we would round up to 4.8 so that it is an even value for our decimal. The next section asks us to calculate based on rounding to 3 significant figures. So let's take a look at all of these here. So the first one says we have this decimal. We want to go to 3 significant figures. So these first 2 zeros are not significant. And we just want to go to We just want to go to here. So we're going to check the next numbers. 7 is greater than 5. So we're just going to round up. That one's not too bad. We just have to know how many 3 significant figures is. The next one, 3 significant figures, that's going to be to the 10th place. And we're going to round down because the next value is a 3. So we're going to round that down to 18.3. For our next one, we want 3 significant figures, so we're going to go to here. Now, this is the similar to the example that we did earlier, where this is a 5. Actually, the 5 ends up just rounding up to 6.88. So because it's an even value, it's going to make it an 8. We have a 5 like that. Okay, this one is the unique one that we did from our last example, but let's look at it one more time here. So we want to go to 3 significant figures. This is 1, 2, 3, and the 5 is going to actually round down to the 8, keeping it an even number. So we've gone to 3 significant figures for all of these. Accuracy and precision. Measurements are precise if they yield a similar result and they're repeated in the same manner. And it's accurate if it's very close or it is the accepted value. So let's look at this instead of A, B, C, let's look at it this other way here. So for C, these 3 are not accurate and they're not precise. So these 3 marks on the bullseye, they're not accurate and they're not precise. So they're not on the bullseye. That means they're not accurate and they're not precise because they're not all in the same value. They're spread far apart. For letter B, these are precise. All of these are very close together, but it's not accurate. We're going for the bullseye. So it's not quite there as far as accuracy, but the precision is there. They're all very close. And this last one, it's accurate and precise. So they are on the bullseye, it's accurate, and it's precise. All of these marks are the same value. Now, when we're talking about a numerical example, I think it might be a bit easier to envision what this means. So let's say that we have a volume of cough medicine that's delivered by 10-ounce dispensers, which is 296 milliliter dispensers. So for dispenser number 1, it's precise but not accurate. So it's all very close to 283 or 284, but that's not accurate. We needed it to be 296 milliliters. For dispenser number 2, it's more accurate. So it's closer to 296 than it is 283. That's 283 is over 10 milliliters of a difference. And here, this is just maybe a couple or a few milliliters of a difference, but it's not precise. This one's 298 and this one's 293. So there's some differences between these. But we are getting a little bit closer to the 296 because we're in the 290s region. For dispenser 3, it is accurate and precise. So there's just a couple decimal places of a difference in milliliters. 0.1 milliliter is hardly a difference in terms of a 10-ounce bottle. So 296.1, 295.9, those are all very close to 296 milliliters. All right, and here are the practice assignments associated with this section.